Let's take a look at the next example. In example 3, suppose we have 4 feet of wire that are to be used to form a circle and a square. How much wire should be used for the square, and how much should be used for the circle to enclose the maximum total area? So for this question, we want to maximize the area. So the area would be the area of the square plus the area of the circle. Let's call a length of the side of the square x, in which case its area would be x squared, plus the area of the circle. Suppose the circle has a radius of r, its area would then be pi r squared. This gives us an expression for the area, but it's now a function of two variables. We have an x and also an r. We want to ultimately reduce this to a function of a single variable, and this is where our constraint equation is going to come in. The constraints is that we have a total amount of wire of 4 feet to use. Where is that wire being used? Well, that wire is what's going to form these shapes. So it's going to form the perimeters of both figures. So essentially they're telling us that the perimeter of both shapes is going to be 4 feet. So the perimeter is going to be equal to 4. That's going to be the perimeter of the square, which is 4x, plus the perimeter of a circle, which we call the circumference. That's 2 pi r. And this is going to be equal to 4. We can take this constraint equation and solve it for one of the two variables. Let's perhaps solve it maybe for the variable r. To get the r by itself, I would subtract 4x from both sides. And then from there, we can divide by 2 pi. Divide by 2 pi. And we see that r is going to be equal to 2 minus 2x all over pi. And this will give us an expression that we can go ahead and stick into our area function. So wherever we have area, this is going to be x squared plus pi times 2 minus 2x divided by pi. And then that whole thing is going to end up being squared. And this gives us a as a function of x. If we can simplify this a little bit, this is going to be a equals, we have x squared plus pi times, if I square this fraction, we're going to have a pi squared in the denominator. In the numerator, we would get 4 minus 8x plus 4x squared. We can cancel the one factor of pi. So we get a equals x squared plus, and now I'm just going to kind of break apart these terms. I'll call it 4 over pi minus 8 over pi x. And then we would also have a plus 4 over pi x squared term. From here, if we wanted to, we do have some like terms. We have an x squared, and we have a positive 4 over pi x squared. We can't add the coefficients in the normal sense, but one of the things that we could do is at least factor out the x squared. So we would have 1 plus 4 over pi x squared plus 4 over pi minus 8 over pi x. And actually, maybe I'll move the x term here, so it's in standard form, decreasing powers of x. So this is our area function expressed in terms of the variable x. So it is a function of a single variable. If we want to kind of think about what is the domain of this function, well, we know that x has to be greater than or equal to 0 for the thing to be a physical situation. We also know that r has to be greater than or equal to 0. If you come back to the expression where we had r, this means that 2 minus 2x over pi has to be greater than or equal to 0. And that means that if you solve it, I'm not going to do the work here, but if you solve it, this means that x will have to be less than or equal to 1. So what is the implied domain for this area function? Well, it's for x's between 0 and 1. So that's the natural domain for this area function. And if we go back to the physical situation, this makes a lot of sense because, remember, how much wire did we have to use? Well, we had 4 feet of wire to use. If you create a square where each side is of length 1, then that's 1, 1, 1, and 1, and that would be all of your wire, which would be all 4 feet, and you would have, in that case, nothing left over for the circle. So, of course, the maximum possible value for the x, which would be the side of the square, would be 1 foot. The very next thing we want to do now is to find our critical numbers. So we're going to need to take the derivative here. So I'm going to take the derivative of the area function with respect to the x variable. dA dx is going to be equal to 2 times 1 plus 4 over pi, and that's going to be x to the first power now, minus 8 over pi. We want to see where is dA dx going to be equal to 0. Looking for our critical numbers. So let's come over here and let's solve that equation. So when is 2 times 1 plus 4 over pi times x minus 8 over pi equal to 0? Well, we would start by adding 8 over pi to both sides. This would give us 8 over pi. We can now go ahead and divide both sides by this constant to get the x by itself. Divide by 2 times 1 plus pi over 4. It's going to be 4 over pi. Divide by 2 times 1 plus 4 over pi. A little bit of fun with fractions. This would solve for x is going to be equal to. So if we try to work this out, what you would get would be the following. This would be like old school keep, change, flip. We're going to have 8 over pi times this 1 over 2 times 1 plus 4 over pi. Notice that the 2's will cancel here. That factor of 2 will cancel. And if I distribute the pi into this parenthesis, we should get the following. X equals 4 divided by pi plus 4. So that's going to be our value of x. So let's come over here. What do we have? Well, we have 0. We have 1. Those are the bounds for this function. And now we have this critical number, which is 4 divided by pi plus 4. we would want to see whether or not that's going to yield a relative max, relative min, or neither. And in order to do this, we could always go ahead and check the second derivative test if we wanted to. Before moving on, though, let's just do a quick double check. This function would not have any critical point of the second type. In addition to where the derivative is equal to 0, we should also want to see if there's any places where the derivative would be undefined. This function dA dx is a polynomial, so it's going to be defined everywhere, so that there won't be any issues of that type. Let's now find the second derivative, because we can do the second derivative test on this. D squared a dx squared would be equal to, it's just going to be a constant, it's actually 2 times 1 plus 4 divided by pi. If I evaluate that derivative at our critical point, notice that this second derivative is always positive. So if our second derivative is positive at a critical point, then that's actually going to produce a minimum value, not a maximum that we were looking for. So it turns out that that is not going to be a maximum at all. We actually have a minimum here. And because of that, what that's going to tell us is that our maximum area is going to occur at one of the endpoints of this interval. For example, if I were to plug, let's say, x equals to 0 into our area function, let's come over here. If x was equal to 0, then this would be 1 plus 4 over pi times 0 squared minus 8 over pi times 0 plus 4 over pi. And that would produce an area of 4 over pi. If I were to plug, let's say, the right endpoint of 1 in, this would produce 1 plus 4 over pi times 1 squared minus 8 over pi times 1 plus 4 over pi. One squared is 1, so this would be 1 plus 4 over pi minus 8 pi plus another 4 pi. The pi terms would cancel because 4 over pi plus another 4 over pi would give us 8 over pi, and that canceled with the negative 8 over pi, and that would leave us with just an area of 1. So if we try to compare what's giving us the largest area here, well, 4 over pi is certainly going to be bigger than 1 because 4 is bigger than pi. It's going to be approximately about 1.27. So if you're curious, and we didn't do this, but we could have plugged in that critical point into the derivative as well. Excuse me, not into the derivative, into the original function, if you wanted to see what the area would have been at that critical value. And maybe we'll also do that as well. So I'm going to come over here. So what would the area for an x value of 4 divided by pi over 4 have looked like? Well, this would have been equal to 1 plus 4 over pi times 4 over pi plus 4 squared minus 8 over pi times x and then plus 4 over pi. if we work this out, one of the things we can do that might be a little bit helpful, instead of just like purely throwing it into the calculator, if you want to do this by hand, notice that this will simplify a little bit. This thing here, if you get a common denominator, this would be pi over 4 over pi, and then this term here, when we square it, is going to give us 16 all over pi over 4 squared. And then this, one of these factors will cancel with one of the things in the numerator. So that should produce 16 divided by pi times pi over 4. Minus over here, we have 32 over pi times pi over 4 plus our 4 over pi. The 16 minus 32, those are like terms, so it's going to give us a negative 16 divided by pi times pi over 4 in that denominator plus 4 over pi. If I continue on trying to get common denominators here, it's a lot of computation. Okay, there's nothing wrong at this point. If you want to put it into your calculator, that's perfectly fine. But if we can do it by hand, it's always a good exercise to go ahead and do so. Pi over 4. This should be plus, getting common denominators, I need to multiply top and bottom here by pi plus 4. That will give us 4 pi plus 16 over pi times pi over 4. When we combine those terms, the 16s cancel. So we're going to be left with 4 pi divided by pi times pi plus 4. The pi's cancel, and so this would leave us with an area of 4 divided by pi plus 4. If you wanted an approximation for that value would be about 0.56, which is smaller than the area that we would get at any of the other endpoints. Okay, so what have we discovered? Well, we found that the maximum possible area occurred when the value of x was equal to 0. So how much should we use for each shape? Well, essentially this is telling us that we're not going to use any square. So x is going to be equal to 0, and our radius of our circle, if you go back to r was 2 minus 2x divided by pi. If x is 0, then this is going to be 2 over pi. So in order to create the maximum possible area, all we're going to do is just simply use a circle. And the radius of that circle is going to be 2 over pi, and that will give us the maximum possible enclosed total area, meaning we wouldn't use any part of the square, just all circle.